So I'm Victor Reijgwart, a student at the Autonomous Systems Lab of ETHZ Zurich, and my main PhD topic is adaptive volumetric mapping. And in the first year and a half, I think one thing that I looked at a lot is how more on the application side of volumetric maps, and specifically how you can use them for path planning and exploration. So today I'll be presenting one recent publication that I think kind of brings everything that we worked on so far together. So this one will be about essentially, I think my computer froze. Okay, it's working again. So what I'll be talking about today is volumetric exploration of large environments, such as, for example, the mines of the DARPA Subterranean Challenge. And some of the use cases for the results that I'll present would be industrial inspection or search and rescue, which is, I think, quite a very interesting problem, both technically and also in terms of how it can be used. So some of the big challenges that we have here are starting with drifting state estimation. So on mobile robots, in real unknown environments, we typically have to estimate their pose using only onboard sensors. And here, over a longer amount of time, it's almost guaranteed that there will be some drift that gets introduced in their original odometry estimate. So in this small video that you saw on the right, I'll see if I can play it again. You could see that this drift in the estimated position of the robot then can also corrupt the map, which eventually could lead the drone to collide with the environment, which is something that for safety reasons we really want to avoid. And then another big challenge is on mobile robots that the computing power is typically very limited, especially on aerial platforms. So in summary, what we wanted to achieve with this work was to create a safe and efficient volumetric exploration framework that is resilient to, or that functions well despite severe odometry drift. So jumping in the system overview, we had two main ideas when developing this. And the first one was that we wanted to create a multi-layered approach that tightly integrated both mapping and planning to make the best possible use of the information that the map provided to make the planning more efficient. And this led us to essentially break down the system into three mapping components and two main planning components, which I'll discuss in detail later. And then the other idea that we had and wanted to essentially try out was to see if we could break up the problem into the local parts and the global parts and solve them quite independently. And I think the results on this were quite surprising to us, at least. So I'll show those later. So starting with the map of the immediate surroundings of the robot, we decided to use we chose a sliding window based approach, where we keep all the point clouds that get integrated into this volumetric map in a buffer. And once they leave this buffer, they get removed from the map again by essentially just inverting or reversing the TSDF integration equations. And the big advantages of this was that it gives us a map that is local in the temporal sense, and therefore stays consistent, even if there's drifting odometry that causes issues over longer time windows. So the big advantage of this was that it allows us to avoid collisions, even if the odometry is drifting, because the objects that we would be able to collide with are typically close to the robot and therefore being observed. So this, thinking about it from a more human perspective, essentially all the obstacles around the robot are still fresh in its mind, so it will not bump into them. Then, of course, we also wanted to have some way to explore, and here we started with local exploration component, which was whose goal was to enable fast exploration of the robot's immediate surroundings. And one recent work by my colleague that I worked together with on this project as well was a graph-based informative path planner, which we used here. And then on the mapping side, we also needed some representation of the everything that the robot observed so far, to be able to make sure that it would explore not just some parts, but really everything. And for this, we used some previous work, or some initial work from my side on Boxgraph, which was a framework that makes it possible to describe the world as a collection of moving volumetric submaps that are aligned through post-graph optimization. So the the advantage of this framework was that it introduces an efficient way to represent the entire world in a volumetric sense, but it still allows the map to be deformed to take information from, for example, loop closures or a larger SLAM system into account. So this loop closure information is not available at the time that the sensor data is initially captured, and only becomes available at a later stage. And then once it is there, we would like to deform the map essentially to improve its consistency. And this is made possible with Voxgraph, even online on small robots. Then for the one challenge for the informative path planner, so for the local planner, was that it computes or it evaluates places to go next by computing the information gain at certain viewpoints that it sampled. And for those of you that are familiar with this approach, you will know that this requires the code essentially to perform really large numbers of lookups in the map, because it typically computes it by ray tracing from a given viewpoint throughout the surroundings to see what the sensor would be able to see at that point. And this approach is already very expensive. It's typically the bottleneck in most volumetric exploration approaches. But for us, if we naively use this global map with all the submaps, it would scale linearly in the number of submaps, which would make it intractable. So what we propose to do instead is that we introduce a second type of map, or a second layer of mapping, which we call the local area, where we initially fuse all the submaps in the global map that are close to the robot together and update this incrementally. So if the maps move, we don't recompute everything from scratch, but we only update the maps that move by removing them and adding them again at this new pose. So this made it comparatively actually very cheap to run. And the big advantage of this was that it allows us to, again, perform constant time lookups for evaluating these viewpoint gains, as if we were working with a single large monolithic map. Then another thing that, or the final thing that we want to achieve, is that we cover the whole environment. So for this, we have a second planner that does the global planning, and it's based on the very common concept of frontiers, with some small modifications to, again, work well with this submap-based global map representation. So instead of recomputing the frontiers over the entire map every time that it deforms, what we propose to do is that whenever a new submap is added to the global map, we extract frontiers on this submap, which is very fast, as the submaps are typically quite small. And then at the global planning stage, the only thing that we then still need to do is to check for those frontier candidates only, whether they are still valid frontier points. So this is very quick. It runs in the order of hundreds of milliseconds, and then allows us to still guarantee global coverage. Once we know where we want to go, which would, for example, be this frontier in the middle, which is red, or any of the 4 frontiers in the right upper corner, we needed some global planning, some global path planning approach. And what we used here was an extension of a previous work of one of my colleagues, Helen, on creating sparse topological graphs and using these for planning, where we create one such topological graph or skeleton for each submap. and then extend the A-star search to be able to jump across submaps. So it would essentially plan in one submap, and then as it reaches an area that's also described by other submaps, it can jump across. And this made it possible to efficiently relocate the robot either from its current position to a new frontier or to an arbitrary waypoint, which could, for example, also be the homing position. Now that I've briefly discussed how the system comes together, let's look at some evaluations to see if it actually works, and especially if our assumptions hold. So we evaluated it extensively in simulation, because there we don't have to worry about crashing the drone, and we have access to more information for evaluations. So what we used was the Unreal Engine 4 together with AirSim and a custom wrapper to interface it with ROS, all of which we made public, or all the modifications are publicly available as open source. And then we ran this because the simulation is very expensive, we ran it on a big server computer with a Intel i9. But I think more interestingly, we also tested it on a real platform, which I forgot to update the name, but it's called Kiwi. And it's a hexacopter from the math team in our lab with OS1 64-beam LiDAR and a small Intel NUC i7 computer. So in simulation, we evaluated on 2 environments, the first one of which is a maze to allow good comparisons to more intuitive comparisons to other planners and other papers. And then we also tested the system in a very large tunnel network like environment. And for the real tests, we by now tested it in quite a few different environments, but I think the most interesting one for this presentation was the LEE garage, because there we have the most metrics. Then we compare against 2 existing approaches, which we considered to be the state of the art of writing, or at the time at least of writing this paper. The first one of those is Active3D, which is the paper from that accompanied the work from my colleague, which introduced the graph-based informative path planner we still reuse here for the local parts, which is based on expanding and rewiring a single tree in an RRT star-like fashion, and optimizes the utility in a global context, and is mainly focused at high performance. So there's no safety considerations there. Then on the other hand, we also compared to GB Planner, which is also a graph-based planner, but the interesting things, or the nice similarities, are that it also uses this concept of local and global exploration, and is mainly focusing on improving safety. So the maze environment measured 40 by 40 by 3 meters, and we simulated 10 runs under each configuration, capped to 15 minutes, because otherwise it would just take too long. I think this already took several days to run. And then we simulate 5 different levels of drift for our planner and the 2 planners that we compare to. So I think the most exciting finding for us was that the global local assumption actually holds up very well. It holds up so well that it outperforms the local approach only, even if there's no simulated drift. So it's not, we'll see later that it's mainly a lot safer, but it's also very fast, and perhaps even faster than other approaches. Then things get most interesting when we start looking at what happens when we simulate drift. So we simulated 5 different levels, starting with no drift at all, up to very severe drift. And the first thing you would see is that the performance of the exploration, so the amount of observed volume over time, holds up much better with the approach we introduce compared to other methods. But most importantly for us was that it remained safe even at high levels of drift. And so to get an idea of how large the drift was, I think state-of-the-art visual inertial odometry systems would have a drift level that roughly corresponds to what we labeled as moderate. So then In the tunnels, we again simulated 10 runs, but because the environment was so much larger, we truncated it to 20 minutes and only simulated 2 levels of drift, no drift at all, and a moderate drift. And then this environment measured 120 by 100 meters and had height differences of up to about 10 meters. So you can see in the pictures that it's essentially a large network of tunnels with some intersections and many dead ends, which are interesting for exploration. So showing you first some qualitative results when we do simulate drift, you can see that the approach works well, and mostly explores using only the local information. But whenever it gets stuck in a dead end, it identifies frontiers and then relocates to them. So at the bottom, that frontier is not reachable due to some temporary corruption in the map due to the drift that we're simulating, but you can see that it then successfully picks another frontier, continues from there. And even though the drift is very large, you see that the map slowly recovers and the planners keep functioning as if there are no issues with the map. I think the code that we were running here for the mapping has been improved quite a bit since this video was made. With the newest versions, you will not see it move around like this anymore. But for us, it was actually quite interesting to see how the planner would do if it moves this much. So in this video, it was still nicer. So then qualitatively, to get an idea of how large the drift or what the effects of the drift would be if we don't compensate for it, is that at the bottom you can see that the map gets completely skewed and you get a lot of double walls and some essentially different breaks in the map. And if we compensate for it using this postgraph optimization with submaps, then you get a map that looks like it should. So again,
sorry, Victor.
Yeah.
Can I ask a brief question about the previous slide? I missed what the colors represent in the right.
I should have mentioned this. So there's many colors because each submap is colored based on a unique ID that it receives, and then this it looks a bit fuzzy, but this is actually good in general because it means that all of the submaps are aligned quite closely together, and then it becomes pretty much random which faces of the triangle get rendered and which corresponding colors are shown because these depend on the submap that the mesh element or the triangle belongs to.
Okay, I see. Thanks.
So here again, thanks for clarifying. So looking again here at how it performs without drift and then with drift, we can see that the approach still performs very well, even if there is no drift. So again, this reinforces the idea that the assumptions are valid. And we can see that when we do simulate drift, it also keeps exploring. It explores a bit slower, but it still explores well. And out of 10 runs, we only had 1 crash, whereas most other planners either got stuck or crashed within the first 13-14 minutes. So then for the real experiments on hardware, we used here odometry from Rovio and flew in the underground parking lot under our lab. And I'll show you a video to give a better idea of what it looked like. So you can see that the robot plans locally and explores what's around it, but also takes a peek into different corners. And from time to time, the global planner kicks in and essentially brings the robot around a car to take a look at what it can see there. I think the camera feed is not giving the best impression of what the robot sees because there's a LiDAR on top that has a 360-degree field of view. But hopefully this gives still the best qualitative idea. So looking at the maps that we got, you can see that it looks like there's a double wall in the top figure, but this is just because the wall is actually, this is a top-down image. There's a section there with a part that sticks out a little bit. but you can see that the map is consistent that we did. And at the bottom in blue, you see the trajectory of the robot in local planning, and in red in global planning. So in conclusion, we propose a method that enables volumetric exploration that most importantly stays safe, even if there's a lot of drift in the odometry. It's also fast and efficient enough to run on real platforms, and it guarantees full coverage. So it will keep exploring until there are no frontiers left. So in other words, that the environment is watertight. And finally, all the code that we used for both planning and also running the simulations is online. So it's available on our GitHub, and if you have any questions, I would be very happy to talk about it. So some future work for planning is that we're almost finished with an extension of this work that allows us to plan for omnidirectional vehicles, so or omnidirectional maps, where for example, one advantage would be that by flying in a vertical mode, we can get through a narrow doorway where it wouldn't be able to go through if it was flying horizontally. And another extension in collaboration with the autonomous robot lab from Reno that now moved to NTNU, that we collaborated with for the DARPA challenge, is a multi-robot version of this planner. So this combines both their work on GB Planner and our work on Global. And that, I think that concludes this presentation. I'll leave this video playing in the background and would be very happy to answer any questions you might have.